Okay, grade 11 chemistry. This is our last video of Unit 1. We're talking about isotopes and a little bit of nuclear science here. We'll start off with just talking about what isotopes are and their role in nuclear reactions. We'll talk about isotopic abundance and calculating atomic masses. Then we'll talk about this interesting trend, because we've been talking about trends in the table. We'll talk about another one, which is stability of isotopes and number of nucleons. Then we'll talk about radioactive dating and radioactive decay, and radiotracers for nuclear medicine, to talk a little bit about some applications of radioisotopes and how they can help us in science and in medicine. First off, what's nuclear energy? Nuclear energy is, obviously enough, the energy of the nucleus. And the nucleus is just the neutrons and protons, right? So we've talked about how chemical reactions involve the electrons, ionic will steal and molecular will share and stuff like that. But when we talk about a nuclear reaction, it's any reaction that involves the nucleus, right? It doesn't have to explode, just has to involve the nucleus somehow. So that's a nuclear reaction. Here's the classic uranium-235 fission. Where a neutron comes in, hits the nucleus, which is all neutrons and protons. That becomes unstable and then splits. It makes 3 more neutrons, and those neutrons go hit other uranium-235 nuclei, and blah, 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 blah. You end up with, explosions or a nuclear reactor, depending on how you manage it. So isotopes. Isotopes, I'm fond of saying, are just things that have too many or too few neutrons. Here, for example, is hydrogen, right? Hydrogen normally just has 1 proton and 1 electron, no neutrons at all. And that's your typical hydrogen. But every so often you'll end up with deuterium. Every 1,000 or so hydrogens, something like that, actually have a neutron in there too. This is called deuterium because it's twice as heavy as hydrogen. Because there's a proton and a neutron. Remember, protons and neutrons make up most of the weight in the nucleus, or in the atom. And it gets this symbol, right? Now, hydrogen is 1,1 because there's 1 proton. So mass of 1 and a charge of 1. Deuterium gets 2,1 because it's a mass of 2, but still has that same charge of 1. Then there's tritium, which is 3,1. And the 3 tells you there's a mass of 3 with only 1 proton. Remember, the proton number tells you which element it is. So all the hydrogens should have a 1, which they do. And this mass number tells you how many nucleons, which are neutrons and protons, are in the center. So 2 neutrons and 1 proton. For some reason, that's unstable. 2 neutrons and 1 proton. There's too many neutrons, right? Too many neutrons. And so this tritium will want to lose a neutron in order to become stable. But it can't just lose it. That's really difficult, to rip a neutron away. It's easier for it to take that neutron, this green neutron here, and flip it into a proton. Turn it into a proton. So the neutron turns into a proton, and it ends up becoming a helium nucleus, because now there's 2 protons. We've changed the number of protons, so now we've changed which element it is. This becomes helium. And if we wanted to write it, it's still got a mass of 3 because that's its mass, but now it's got 2 protons, so 2 protons, making it helium instead of hydrogen. Right, it went from hydrogen 3,1, it went from what we call hydrogen 3 to helium 3. Because this neutron turned into a proton. The charge has to go somewhere, so the neutron turned into a proton. What happens is an electron is created, literally created out of nowhere, just from the energy, and gets sent out as a beta decay. So that electron gets a very high amount of energy and just goes flying off. But yeah, this is matter coming into existence out of nowhere, which is kind of cool. And off it goes, and that's in this transformation of tritium to helium-3. So these 2 are what we call stable. This one, unstable, just the wrong number of neutrons. Here's carbon. Carbon-12 is the classic carbon atom. 6 protons, 6 neutrons, because carbon is number 6 in the periodic table, so it's always got 6 protons. This is carbon-13, which has the same 6 protons because it's carbon, but now it's got an extra neutron, right? An extra neutron. So that's where the 13 comes from, because 6 plus 7 is 13. Carbon-14 has 2 extra neutrons compared to carbon-12, and this one is unstable. Carbon-14 is unstable. It has 8 neutrons. And it also decays through the same process, beta decay. One of the neutrons, which is too many of them, too many neutrons, will turn into a proton, and now the carbon has changed from carbon to nitrogen, because carbon is the one with six protons, right? 6 protons, that's carbon. Nitrogen is the one with 7 protons, and that's nitrogen. Because that's how we arrange them in the table, by the number of protons that they have. Remember this, keep in mind. So those are isotopes. These are all carbon because of the number of protons, but they're isotopes of each other because there's different number of neutrons. So carbon 12, 13, and 14 are all isotopes of carbon. Hydrogen 1, 2, and 3 are all isotopes of hydrogen. The decay process is technically a nuclear reaction because the nucleus has changed. Right? Nucleus has turned into a different element. Something has changed about the nucleus. That is a nuclear reaction. We'll see carbon again when we talk about carbon dating. So at the very end, we'll circle back around and talk about how this lets us date different things. So we're on to the next section, which is isotopic abundance. I'm going to change some stuff here. So we're talking about isotopic abundance. Little keep in mind here, any visible sample will contain billions and billions and billions of atoms. So these ratios that we're about to see are very exact for pretty much anything that you'll find on Earth, because there are billions and billions of atoms. So we'll talk about isotopic abundance. So basically, if you pick up something like, say, this steel wool, right? This steel wool, it's got iron atoms in it, lots and lots of iron atoms, billions of iron atoms, well, quadrillions of probably more than that, quintillions of iron atoms in this thing. Some of those iron atoms have a certain number of neutrons. Other iron atoms have a different number of neutrons. So there's isotopes in here. And just like with carbon, where there's 2 stable ones, carbon-12 and carbon-13, there's different stable isotopes of iron and different stable isotopes of lots of different elements. So here, for example, is silicon. Silicon, you can find it in the table. It's number 14. You see that atomic mass is like 28. So a lot of it is silicon-28. The blue is silicon-28, which is 92% of all the silicon that we find on Earth is silicon-28. And about 5% of it is silicon-29, and about 3% of it is silicon-30. So there's this abundance of different isotopes. And that's not like we'll find a chunk of silicon somewhere and that particular chunk is 28 and a different chunk somewhere else is 30. No, every chunk we find is 92% silicon-28, 5% silicon-29, and 3% silicon-30. So this kind of suggests that they all formed at the same time in the same place, kind of thing. So silicon's an example of one where there's a majority of one particular isotope. Carbon is another example. 99% of it is carbon-12, and only about 1% of it is carbon-13. But other ones have a little bit of a fancier distribution. So rhenium, for example, rhenium comes in 2 stable forms, rhenium-185 and rhenium-187. The 185, there's about 37% of the rhenium is rhenium-185, and about 63% of it is rhenium-187. So sometimes they're mostly one thing. Sometimes they're split. Platinum's an interesting one. It's got kind of a 3-way split between the 195, the 194, and the 196, and then there's a little bit of 198, a little bit of 192, and a tiny sliver of 190, because the 190 is radioactive and will decay and turn into something else. So that's platinum. It's kind of neat. Platinum's atomic mass is a reflection of this, because it suggests maybe that there's a lot of 195, but it's just that there's kind of equal 196 and 194, pulling it one way and the other way. Speaking of atomic mass, we want to calculate atomic masses, and atomic masses are calculated as a weighted average of the individual masses. And what is a weighted average? Well, us teachers, we love weighted averages. Here's an example of a weighted average for some random student. Did okay at the quizzes, did really well at the exam, but didn't do so hot at the term paper. 76 on the term paper, but the term paper is worth 45% of the mark, whereas the exams were 35% of the mark, and the quiz is worth 82% of the mark. So what did the student get as a final mark? How do you calculate it? Well, you assign a weight, right? A weight, right? The weight or the weighing factor here is how much of the total the mark should represent. And so to calculate this, you would go 82%, right? 82, the mark, times the weighing factor is 0.2. Then we'll add the 90% for the exam, times the weighing factor, 0.35, plus the 76 times the weighing factor of 0.45. So let's run it through our heads for a second. Let's see what we expect. Probably here, these are pretty close together. I'm thinking this will be right around 80, right around 80%. So let's have a look. 82 times 0.2 plus 90 times 0.35 plus 76 times 0.45, 82.1. 82.1% would be this student's final grade in this course. So, they did really well at the exam, but really bad at the term paper. Well, not really bad. 76 is a good mark, but relatively bad in the term paper, and so it kind of evens out to an 82. Same thing happens with isotopes. We use a weighted average to calculate it. So here, for example, is iron. Iron has 4 stable isotopes, 54, 56, 57, and 58. 54, 56, 58. And here are the percentages. It's about 6%, 5.8% iron 54. It's about 90% iron 56. Right? It's about 2% iron 57. And it's about 0.3%, a very small amount of iron 58. And these are the atomic masses. 53.9396 is the mass of iron 54. 55.9349 is the mass of iron 56. 56.93 is iron 57, and 57.9 is iron 58. Note that the isotope masses, the actual masses, are pretty close to that number. This is number 54. 54, so there's 54 protons and neutrons together, but the mass is like 53.9. Pretty close. 56, pretty close to 55.9, 56.9, that kind of thing. And so you do the same thing. You add them up the way that we added this. And each of these represents one mark, right? Each of these this times the weight represents one of the marks. Like that first one is the quizzes, the second one is the exam, and the third one is the term paper. Well, same thing here, right? Each of these little guys represents one isotope. Each of these little guys represents one isotope. And then we add them together, and you get an average, which is behind my face here, and that average is 55.85 AMU, and that's where iron's mass on the table comes from, which you'll see there says 55.85 AMU, or 55.85 grams per mole. Let's do a practice problem. Let's actually do one together. Here's the masses and the abundance of different isotopes of magnesium. We have 3 isotopes, 24, 25, and 26. Most of the magnesium is magnesium 24, but there is 10% 25 and 11% 26. So the first thing I like to think of is, where do I predict this magnesium is going to sit in terms of an atomic mass? Well, if it's mostly 24, we expect the mass to be pretty close to 24, but the other two are higher up, so it's going to be, predict prediction 24.6 something, right? 24 point something. Not sure, but it's going to be 24 point something or other. Now to figure out the actual thing, remember how we did it back here? We had a value for each little mark and then the weighing factor. We'll do the same thing. We'll have a value for each isotope and the weighing factor. And what we can do is convert these percentages into weighing factors. You just do that by dividing it by 100. So that's 0.787. That is that one is 0.103, 0.1013, and 0.1117. Let's shrink that a little bit. There we go. There's our weighing factors. Right, there's our weighing factors. And here's our masses. So we do the exact same thing we did back here, or we do the grades times the weighing factor, or here the masses times the percentages. And we can actually calculate it. So, we take this mass and multiply it by that number. And we take this mass and multiply it by that number. And we take this mass and multiply it by that number. And then we add them all together. Okay, so what does that look like? Let me actually type that out. It's going to be 23.98504 times 0.787, which we got from the percentage, right? That's our first isotope and its first percentage. Then we have 24.98584 times this number here, 0.1013, plus, and then the last one here, 25.98259 times 0.1117, right, times 0.1117, and we'll add them all together and we'll get equals, we'll just put through the calculator and see what we get. So 23.98504 times 0.787 plus 24.98584 times 0.1013 plus 25.98259 times 0.1117. Nope. Calculator's throwing an error at me. That seems good. There we go. I get 24.3. 0.305. 3095 AMU, well, or just U, or if we round it, right, maybe 24.31 units, something like that. Hey, it matches our prediction. It's a little bit more than 24, which makes sense. All right, makes sense. That's a bit more than 24. 24.31, and you can even check it on the table, right? On the table, we have 24.305 on the table, so yeah, pretty much bang on the money. And that's how you do these calculations. It's very much like doing one of these weighted averages, because it's kind of what it is. Yeah, so that's done talking about atomic masses and calculating atomic masses. Next up, we're talking about this cool stability trend about even and odd nuclei and nucleon numbers. So I'm going to pause. This is a trend that's very, very cool to me, even in odd numbers of nucleons. The reason that it's cool is it suggests that the nucleus itself has levels of organization, kind of like electron shells do. Remember, electrons like to pair up? Well, it turns out that an even number of protons or an even number of neutrons is more stable than an odd number of protons or an odd number of neutrons in a nucleus. And here's the proof is when we look at our stable nuclides, our stable isotopes, we see that when there's an even number of both protons and neutrons, even protons, even neutrons, there's 168 of those. And if it's an even number of protons and an odd number of neutrons, or an odd number of protons and an even number of neutrons, it's about the same. So it doesn't seem like one or the other is preferred. And then an odd number of protons and an odd number of neutrons, there's literally only 4 stable nuclides that have odd number of protons and odd number of neutrons. And those 4 stable isotopes are hydrogen 1, lithium 3, boron 5, right? Hydrogen 1. Sorry, that would be hydrogen 2, wouldn't it? Yeah, so hydrogen 2, which has 1 proton, 1 neutron. Boron 10, because 5 protons, 5 neutrons. And lithium 6, because 3 protons, 3 neutrons. And nitrogen 14, which is 7 protons and 7 neutrons. So those are the only 4 stable odd nuclides. There's one radioactive isotope that has an odd feature, but it is like there's a lot of radioisotopes that have odd ones, but there's one that's we've never seen it decay ever. So we know that it's unstable, but we've never seen it decay. So it's just like really long lived. I forget what it is. It's like a molybdenum something or other, I'm pretty sure. Yeah. Anyway, yeah, so if it didn't matter, if odds and evens didn't matter, we'd expect 25, 25, 25, 25, because that's, the same probability for that. But no, we get 60% of them being even. So the thought is that an even number is just kind of good, both for protons and for neutrons. Yeah. Out of these 4 isotopes, these 4 odd isotopes, only nitrogen 14 is the most common in terms of nitrogen, right? Like almost all the nitrogen is nitrogen 14. For boron, most of the boron is boron 5, which has 3 protons but 2 neutrons. Hey, an even number of neutrons. And most of the lithium is lithium 7. Sorry, not boron 5. Most of the boron, if we look at boron on the table, is boron 11. So 6 neutrons. And most of the lithium is lithium 7, which has 4 neutrons. And most of the hydrogen is hydrogen 1, which doesn't have any neutrons at all, just the 1 proton. And this is where our isotope ratios are so interesting, because, for example, if we look at gallium here, gallium 69 is stable, and gallium 71 is stable. It's about 60% one and about 40% the other. Gallium 70 decays in 21 minutes, 21-minute half-life. It's actually, out of all of these, the shortest lived isotope is the one that's right between the 2 stable ones. So it really shows you that that the number of neutrons matters. So gallium has 31 protons. Gallium 71 would have 40 neutrons, which is an even number, and gallium 69 would have 38 neutrons, which is also an even number. So the 2 even numbered ones are stable, and the odd number ones are not. Silver does the same thing. Silver has 47 protons. Silver 107, which would have 60 neutrons, is stable. Silver 109, which has 62 neutrons, is also stable. But silver 108, that odd number of neutrons, no, not going to happen. Here's bromine, right? Bromine is pretty much dead split, 50-50, between bromine 81 and bromine 79. Now, bromine has 35 protons, so this one has, what would that be, 44? Yeah, 44 neutrons, and that one has 46, an even number. And same thing with chlorine. Chlorine has 17 protons, and it's a split. About 25% of it is chlorine 35. 25% of it is chlorine 37, and 75% of it is chlorine 35. It seems like even numbers are good. There's kind of a cool trend that we notice in the periodic table. That kind of helps explain some of this decay. We see the same thing when we looked at isotope ratios back here. Rhenium, there's 185 and 187. Those are both stable. So that's that cool stability trend. Next, we're going to talk about radioactive decay and radiometric dating. So I'm going to pause for a sec. now that we know about stability and things like that, this is actually a great place to talk about radioactive decay, because you can see this stuff here. It says half-life, half-life. So for gallium-70, right, that middle ground, I said 21 minutes was the half-life, and it decays by beta negative most of the time, and it turns into germanium-70, which germanium has 32 protons, and germanium-70 would have an even number of protons and neutrons. So that is much more stable, or predicted to be much more stable than gallium-70. And what does that 21-minute half-life mean? It means that after 21 minutes, half of your sample of gallium-70, or half of the gallium-70 in your sample, will become germanium-70. After two half-lives, after 42 minutes, we'll end up with a quarter, right? A quarter of your gallium left, and 75% of it will be germanium-70. After another 21 minutes, which would be 63 minutes after you take your first sample, then you're down to what, 12.5%, right? You're down to 1/8 of your original gallium is still gallium-70, and 7/8 of it is germanium-70, and so on and so forth. So different isotopes have different half-lives, and the reason that it's this perfect 50-50, 50-50, 50-50 thing is that it's based on probability. Each individual atom has this percent chance to decay at any given time, and over time the total percentages build up and up and up and up and up. But if you have a lot of atoms, then they're going to, there's more long-lived ones in there, because there's just more of a chance of finding a longer-lived one. It's perfectly 100% based on probability. We can't detect when the thing is going to go. There is no such thing. It's based on kind of the wiggliness of the nucleus, and if it just wiggles the wrong way, it decays. And the probability of it wiggling the wrong way is different depending on the isotope. But yeah, it doesn't give us any signals that it's going to decay. It just does at some point. But remember that any visible sample has billions and trillions and quadrillions of these things. So the overall half-life becomes pretty much exactly what you see, right? Because if you take a percentage, one single thing is maybe not going to go the way that you want when you're talking about probability, but when you have a billion examples, that will eventually go the way you want. This is how casinos make money, right? One person might win, but other people are going to lose. The same idea. So that's radioactive decay. Here's a few different modes of radioactive decay, right? They'll try to get to a more stable thing. If they have an odd number of protons, they might want to get an even number of protons. If an odd number of neutrons, they might want to get an even number of neutrons. If they have too many of one thing, they might even try to kick it out. So here's a few different decay modes. Alpha decay, they kick out essentially a helium nucleus, so 2 protons and 2 neutrons that are still bound together. It just gets kicked right out. Remember I talked about how there's this thought that nucleons arrange themselves a bit like electrons, where pairs are very stable. Well, 2 is the smallest even number, so 2 protons, 2 neutrons is incredibly stable. That helium nucleus is super, super, super stable for its size, so that's common for it to kick out. There's beta decay, where a neutron turns into a proton, and you get an electron created from thin air. Just energy turns into an electron, and the electron flies away. Then there's positron emission, which is the opposite. Proton turns into a neutron, and you make a positron. A positron is antimatter. It's literally an electron with a positive charge. If it hits a normal electron, it'll just annihilate, go back to energy. Because it came from energy, it can go back to energy. Electron capture is a proton turning into a neutron again, but instead of creating a positron, it happens by absorbing an electron. So the nucleus actually grabs an electron from somewhere. It requires a high energy electron, but it does happen sometimes. Notably, this happens in supernovas, or just before the supernova. There's a gamma emission here. This is like, there's not a, it actually doesn't change the nucleus at all. But the idea here is that maybe the nucleus is in a little bit of the wrong shape, and then it snaps into a better shape, a lower energy shape, and out comes a gamma ray. So we see this. This is used a lot for radioactive medicine, for certain radiotracers, because it's not as harmful as other forms of radiation. And then spontaneous fission is the last one. Fission is the nuclear reaction word for splitting apart. And so sometimes when you have a big enough isotope, it just kind of cracks in half and creates neutrons. So you get two smaller nuclei and a bunch of neutrons coming out. These types of isotopes are actually very important for starting up nuclear reactors, because we want fast neutrons. Yeah, so there's a bunch of different ways that these things try to get stable. I'm not going to quiz you on them or anything, but there are different ways for it to happen. And here's a big old graph of what kind of decay happens depending on what kind of isotope it is. So here's the number of protons and here's the number of neutrons. Protons versus neutrons. This line is a 1-to-1 ratio. The 1-to-1 ratio is this line here. You can see that in the lower thing, the 1-to-1 ratio is really very, very stable. When we talked about how, like, even when you have the odd nuclei, they're still stable when we have, 1 proton, 1 neutron, 3 protons, 3 neutrons, 5 protons, 5 neutrons, and 7 protons, 7 neutrons. But then eventually you need more neutrons for some reason compared to protons, so the line kind of deviates upwards. If you've got too many neutrons, it'll decay by beta negative. That's what carbon-14 does. It turns a neutron to a proton to become nitrogen-14 and become stable. If it's got too few neutrons, it'll go the other way. A proton will turn into a neutron, and that's beta positive emission. That's this orange one here. When you get really heavy, you can get that alpha decay where they kick out 2 protons and 2 neutrons. In some of the really particularly heavy ones, these green ones, you end up with that spontaneous fission. And then there's a few other funky ones, like kicking out a whole proton or kicking out a whole neutron, which happens at the edge cases. Right? When you have too few neutrons, you can just kick out a proton if you want. If you have too many neutrons, you can just kick out a neutron if you want. But that's the edge cases. By far the most common one is beta negative and beta positive emissions. Yeah. And then the black is all the stable ones. You see these numbers, 6, 14, 28, 50, and 82. Those are called the magic numbers. That's where there are particularly stable amounts of nuclei, of nucleotides. So, sorry, not nucleotides, of nucleons. So 6 protons or 6 neutrons seems to be quite stable. So carbon, 6, 6 is very common. 14 is particularly stable as well, which is silicon. 28 appears to be quite stable, which is nickel. Nickel is a very stable nucleus. 50 and 82 as well. Yeah, so it's kind of an interesting thing. There's a lot of cool physics, chemistry interaction when we talk about this nuclear type stuff. Yeah, so we use that. We use those decays to do radiometric dating. Here's how it works. There's a lot of C12. By far, almost all the carbon you see is C12. There's about 1% C13, and there's a tiny, tiny bit of C14. That C14 is radioactive. It decays through beta negative decay. It turns into nitrogen-14. Nitrogen-14 is stable and will not produce radiation. So this happens on a half-life of 5,730 years. So after 5,730 years, whatever sample you had is going to be half as radioactive as it was before, right? Because all of the half the radioactive carbon has turned into not radioactive nitrogen-14. And so you can actually measure how much radiation is coming off the sample. You can see how much carbon is in it, and then you can use that to predict how much of the carbon-14 is left in the sample. And that's how radioactive dating works. Here are some known ages of things, because we've got a history that stretches back pretty far now. You take a tree ring and you count the tree rings back, and then you see the wood, which is carbon, and you can see how much radiation it's giving off, and it matches the predicted curve, the 5,730 year decay curve, really, really, really well. So you can see here, this is the radioactivity from 1 at the start. When it gets to 0.5, we are right at that 5,700 year mark. Right at that 5,700 year mark. And then it keeps going, right? Another 5,700 years later, it'll be at 25% of the original, and then 12.5, and then 6.25, and then, on and on and on and on. So we can estimate the age of something just by putting a Geiger counter there and seeing how much radiation is coming off. So there's this predictable decay in the decay, this predictable reduction in radioactivity, and it helps us figure out the ages of certain things. Carbon's a very common one because carbon-14 is taken up by living things, so we can use it to date things that used to be alive, like trees or fossils and things like that. It's only good for a couple 100,000 years. Past that, we have other isotopes that we can use that have much longer half-lives, so like potassium argon and other things like that. There's lots of different dating methods, and you can look that up yourself if you feel like it, but that's how radiometric dating works. We have one last thing to talk about, which is radiotracers for nuclear medicine. So, radiotracers. Radiotracers, one thing to keep in mind is that radionucleotides, the ones that are radioactive, they have exactly the same chemistry as other versions of the same element. Carbon-14, right, carbon-14 acts just like normal carbon. It's a little bit heavier, but that doesn't do a lot to its chemistry. Because it's still got the 6 protons, and it's still got the 6 valence electrons, it'll make 4 bonds, and all this other stuff we've talked about. So, you've got carbon-14 in your body right now, and it's being used as normal carbon to build your structures and stuff like that. So you are slightly radioactive. So we use this concept of having the same chemistry but a different radioactivity to do stuff like this, where we will put a radio tracer on something. This, for example, is a glucose that's been what we call tagged with a fluorine, and that fluorine is a radioisotope of fluorine, fluorine-18. It's a half-life of about 2 hours. The fluorine-18, fluorine is atomic number 9, so there's 9 protons there. So fluorine-18 is 9 protons, 9 neutrons. That's unstable. It's an odd nucleotide. So every 2 hours, it decays, and it decays by positron emission. So it creates a positron, and the positron hits an electron, and they annihilate, and you get radiation coming out. That means that if you take glucose and you put fluorine-18 on it, and then you make the person eat the glucose, everywhere in their body where the glucose goes, you'll get a radioactive signal from it. And it's a very specific radioactive signal that we know that energy comes from that specific radioisotope. And that can be combined to make this scan. You see this scan of a person. You see that the brain is using a bunch of the sugar went up to the brain. Other parts of the sugar went, in the liver and the intestines and the stomach and stuff like that. This is kind of where you expect this sugar to go, because these things use a bunch of energy. But then you got down here, you got this little spot down here. Right? You got this spot. There's a lot of glucose that went to the rectum, which suggests that there's something there that's using a bunch of sugar that shouldn't be. So that might be a tumor, because there's something there using a lot of sugar that compared to baseline, basically. The liver as well. So you see, this is called a PET scan, positron emission tomography scan. And this is them actually injecting the radioactive tracer into the person. It's kind of cool. The syringe is actually shielded against radiation. So yeah, you actually get an injection of radioactive material for it. There's a bunch of different isotopes for this. This is a very common one for tumors and stuff. You can also get radioactive iodine put into you, because there are certain cancers like thyroid cancer that will like to take up radioactive iodine, and you can trace it around the body. Here's another really common one. It's called 99M, technetium 99M. It's got a half-life of 6 hours. It's created specifically in old research reactors, really old research reactors. So you see these years that they started is like 1957, 1961, 1965, and stuff like that. One of the biggest producers was actually the NRU in Canada in Chalk River, but it got decommissioned recently. So the world lost a bunch of supply of this important radionucleotide. Um, this radionucleotide. And this is the chemical that they would put into you to trace to make this kind of scan. And we were making a bunch of it in Canada, but then we decommissioned that reactor. So I don't know what they're going to do when more of these reactors start going offline. But someone's got to figure something out there. That's long enough. Just a recap, we talked about nuclear reactions and isotopes. Isotopes having too many, too few neutrons. We talked about isotopic abundance, that different elements have different proportions of their different isotopes. We talked about how to calculate atomic masses by doing a weighted average. We then talked about even and odd and how the number of nucleons can affect stability. We talked about different types of radioactive decay, different modes of decay, and how it helps it get back towards this stable black line there. And then radiometric dating, like carbon dating you might have heard of. And we just finished talking about radioactive tracers. So that's long enough. That's like 42 minutes of content. That's the last bit of this unit's the last bit of content for this unit. I'll see you guys in class, I guess.